ProbeLogue before the probe. Welcome to another episode of Probe DD, where we probe right into the problem. It's May 1st, 2025, day 32 of dry docking. Today's highlight, the DNV class survey, including the blackout test and automatic generator startup. But the power management system isn't cooperating. We experience more blackouts than necessary, and every trip takes a toll on our electronics.
So what are you doing now? Reset. Reset.
I was playing before and I blocked the start command.
Это технician, он нам настраивает новую систему, я вот он вчера там подключал. Я не...
Sudden power loss, voltage drops, frequency instability. In this episode, we'll see exactly why power electronics hate poor power quality. 4 devices were damaged. First, the frequency transducer of DG1. Second, Framo Power Pack 4's power transducer. Third, the steam pressure instrument panel at ECR console. And fourth, a critical one,
Can you press this?
the boiler's high water level trip amplifier. That last one is non-negotiable. We need steam before sailing in 3 days.
I proved it manually now.
Why?
I have to see why it didn't send it by itself, this close command.
Now that the DNV survey is complete, we shift our attention to the oil-fired boiler. A general fault shows up on the IAS alarm page. The details? They're at the boiler main control panel. The alarm reads, low water level. Let's probe into it.
I saw the name immediately. I knew this is the guy. Again.
See you next time, mate.
See you.
Good
Thank you
luck.
very much.
Bye.
Now probing, checking of level transmitter and switch. For the first step, we tried pressing the reset switch, hoping it might clear the fault, but it didn't. So we headed to the field instruments to check their condition. This is the A7C2 low water level switch. And behind it, the A10 water level transmitter. First, we check the A7C switch. Resistance across terminal X6 1 to 2 reads 4.2 ohms. That's good. It confirms the normally closed contact is intact. Resistance across X6 3 to 4 is 00 mega ohms. Also good, this side is normally open. Voltage from X61 to ground is around 115 volts AC. X62 to ground is also around 115 volts. Since the contact between 1 and 2 is closed, both terminals have nearly the same potential to ground. The switch is fine now that we have normal water level inside the boiler. Next, we check the A10 level transmitter. Supply voltage reads 19.21 volts DC. Voltage is present. The nameplate input voltage rating is 24 volts. Let's now probe its process signal current in milliamps. The multimeter should be connected in series between the power source and the transmitter's positive terminal. We removed the positive wire from the terminal and inserted the probes accordingly. There was some issue with the black probe connection. So we added an alligator clip to stabilize the contact. Now we have a reading.
50% yan. 50 plus. Hindi na maganda yung connection ko kanina eh.
The current is 12.86 milliamps DC. That's about 50% of the level range. Now probing, simulation of too low water level alarm. To simulate the alarm, we disconnected the wire from terminal X61. After the preset time delay, the too low water level alarm became active. This mimics the actual condition where water level drops too low, causing the magnetic level switch to open its normally closed contact. This breaks the signal to the Z2 input of timer relay 17K7F. After its off delay expires, the timer's auxiliary contact 15-18 opens. This de-energizes relay 20K1F. Its normally closed auxiliary contact 21-22 then closes, activating the too low water level alarm lamp and triggering the safety loop that shuts down the boiler. After the simulation, we reconnected the wire to terminal X61. The too low water level alarm returned to normal. Now probing, checking low water level circuit. We started with the 42H3F indicator lamp for low water level. Using the boiler electrical schematic, we traced backward to find what's keeping the alarm active. The lamp is powered through the normally closed contact of relay 20K5F terminals 21 to 22. According to sheet 20 section 5F, we located the 20K5F relay in the circuit. Going upstream, we found it's controlled by the normally closed contact of 17A6B trip amplifier terminals 4 to 5. This is the 42H3F lamp, and this is the 20K5F relay. The water level was already confirmed to be normal. I was asked to inspect the water level controller connected to the level transmitter. We tried lowering the set point from 130 to 100, hoping to clear the fault, but it didn't work. So we reverted it back to the original setting. With the alarm still active, we manually depressed the contacts of relay 20K5F. The alarm cleared and the circuit returned to normal. That confirms the output side is okay. Which means something in the input side is triggering this abnormal alarm even though the water level is already normal. It's time to probe deeper into this circuit, starting with the 20K5F relay dedicated to the low water level tag. This leads us to its upstream trigger, the trip amplifier's limit switch. Ultimately, we'll probe both trip amplifiers and find out why their displays are showing malfunction. Now probing, doubling down on the trip amplifiers. From the output side of the alarm, we traced all the way back through the schematic. From sheet 20 to sheet 15. There we found the 15K7F relay, labeled as the reset relay. This is a good example of multi-page backward cross-referencing. But there wasn't much to gain here since we had already used the reset switch earlier and confirmed its working. So we moved to sheet 17 to look for the core of the issue. The 17A6 B-trip amplifier, at sheet 20, we saw its NC auxiliary contact 4 to 5. Which, at sheet 17, is configured as relay to a limit switch. Notice that the amplifier's display reads around 50 to 50.2. This closely matches the water level transmitter's output, which we measured earlier as 12.86 milliamps. That aligns with a 50% level on a 4 to 20 milliampere scale. If our actual water level is around 50% and the set point for the alarm is 36%, then why is the alarm still active? For starters, if the level falls below the 36% set point, low level alarm will be triggered. At this moment, NC contact 4 to 5 is open since we removed the 17A6 B-trip amplifier. Around the same time, the too low water level alarm also became active after its designated time delay. This second alarm is also tied to the 17A6 B-trip amplifier, specifically to its limit switch 6 to 7, also known as Relay 1's NO contact. Let's review the set points. Relay 2 was originally at 20 and has been increased to 36. Relay 1, on the other hand, was adjusted from 40 down to 30. This setup makes sense. As the water level drops, the low alarm should activate first. If the feed water pump fails to restore the level, then the too low water level alarm will activate and shut down the boiler as a final safety trip. For clarity, we removed the amplifier for a good view. Now let's probe Relay 2 on 17A6B, the NC contact assigned to low water level. Terminal 4 to 5 shows 20 mega ohms of resistance. This is considered open. Voltage at terminal 4 to ground is just 31.3 volts AC. That's way below the 220 volts needed to energize Relay 20K5F. Now let's check Relay 1, the NO contact assigned to too low water level. We used K7F's Y1 and terminal X116 for a hot probe test. The potential was just 3.2 millivolts AC, meaning the contact is closed. Then we confirmed it with a cold probe. Resistance equals 1.6 ohms. That also confirms a closed contact. To complete the loop validation, we check between K7Fs Z2 and Y1. This includes the relay 1 contact at 6 to 7 and the level switch 17A7C. The total resistance was 2.6 ohms. That confirms relay 1 is good. The too low water level loop is intact. Here's my initial prognosis. The transmitter signal is good. The level controller receives it. Both trip amplifiers 17A2 and 17A6 are also fed with that input. But are the trip amplifiers processing the signal correctly? And if yes, are they converting it into proper output through contacts 4 to 5 and 6 to 7? So why is 4 to 5 open? These questions can only be answered once we replace the suspected defective amplifier. Let's prove it once we find an exact spare. First, we'll check the TM Master Spare Parts database to see if we have a replacement available. We're looking for a trip amplifier type 2231.
Trip amplifier. We have one in B34.
Aha!
We have here is it on? Let's see.
Now probing, exploring 17A2B trip amplifier. We're now looking into the 17A2B trip amplifier to understand the cause of its erratic display and to see whether it affects the low water level alarm. At first glance, we might disregard its role since this amplifier is assigned to monitor the high water level. It's not directly connected to the 17A6B amplifier, which handles the low water level alarms. But let's not rule it out yet. A deeper probe reveals that both trip amplifiers 17A2B and 17A6B are in the same signal loop. The level transmitter sends its analog signal through both amplifiers in series before it reaches the level controller input. Let's observe the display of 17A2B. Earlier, it showed random values, sometimes H, sometimes just a dash. Now, it's showing -2. We tried adjusting its settings, but the unit isn't responding at all. No key press is registering, and we can't access any parameters or set points. This kind of failure is consistent with the recent blackout event. The same one that damaged multiple electronics on board during PMS commissioning and blackout tests. We'll now replace this defective 17A2B trip amplifier with a new spare. And we hope the next blackout won't take it down again. But we're not done yet. The alarm hasn't cleared. That means we need to configure the parameters and settings of the new trip amplifier installed under the 17A2B tag. And we also need to check if the blackout affected 17A6B's internal settings. Once again, the blackout has delayed our probing. But now it's time to verify something we suspected earlier. Does the 17A2B trip amplifier affect the low water level alarm signal? Let's probe it. First, we measured the input voltage at the 17A2B socket. It reads negative 22.83 volts DC with reversed polarity. Then we check the input voltage at the 17A6B socket. Result, no potential detected. So now let's take the old 17A2B trip amplifier, even though it's defective and shows erratic values, and place it back in its original socket. Now we measure again at 17A6B. This time we get 22.84 volts DC at its input. But once we remove the 17A2B again, the voltage drops back to zero. That proves it. The 17A2B trip amplifier is electrically linked to the 17A6B signal path. Its presence affects the downstream input, and that's why it's directly involved in the water level alarm circuit. Now probing configuration of trip amplifiers. Before we begin the configuration, let's review the trip amplifier's outline settings. These values are critical when commissioning a new unit, not just to follow factory defaults, but to restore the vessel-specific configuration. For the 17A2B trip amplifier, we'll only be using relay 2. A normally closed contact for the high water level. First, we labeled the relay tags on the cable duct cover for future reference. After some earlier swapping during testing, we now remove both trip amplifiers. Then we install 17A2B, the new unit, and 17A6B, the original one, in their proper positions. After switching on the reset, the alarm cleared. But only for a few seconds. The low water level alarm came back. That's expected because the new 17A2B is still unconfigured and 17A6B not yet checked. So first we'll verify the configuration of 17A6B, starting from relay 1, relay 2, the analog input and application parameters. At relay 1, the set point was found at 10.0. It should be 30. After setting the new value, we saved it by pressing up and right together. Some parameters were also incorrect. For example, the direction was set to increase when it should be decreased. At relay 2, the set point was found at 80.0. It should be 36.0. Again, the direction was wrong, also set to increase instead of decrease. After completing the 17A6B configuration, we pressed reset. This time the fault was cleared. All other settings were confirmed to be correct. Now, for the 17A2B trip amplifier, we labeled the relay tag. And proceeded with full configuration from relay 1 to the application menu. After everything was set according to the outline, configuration is complete. For the recap of our probing experience, during DNV's blackout testing, several electronics were damaged, including the trip amplifier linked to our low water level alarm. We confirmed normal water level and verified that both the level switch and transmitter were working. A simulation showed the alarm circuit was functioning, so we traced the fault deeper to trip amplifier 17A6B. That's when we noticed something unusual. 17A2B, which monitors high level, had an erratic display. Probing revealed both amplifiers share the same analog loop. Removing 17A2B killed the signal to 17A6B. Reinstalling it brought the input voltage back. We replaced 17A2B and reconfigured both units, correcting set points and logic directions. After a final reset, the alarm was cleared. After replacing the 17A2B trip amplifier and restoring all configuration parameters, the oil-fired boiler is now up and boiling. Alarm cleared, logic confirmed, system back in control. This wraps up day 32 of dry docking. Thank you for watching, and as always, keep on probing.